All right, so I figured this would be a good topic because a few different reasons why. Uh, One of the concepts that a lot of people run into with RMS, root mean square, in electronics is when they're doing a sound system, an audio system, stereo, DJ, car sound, car stereo, whatever it is. You have RMS power ratings on all your equipment, whether it's speakers or amps or all that stuff. What does that actually mean? And RMS stands for root mean square. Root mean square sounds like a whole lot of math. It sounds like a high school algebra class condensed into 3 letters. But we're not going to talk about math. I'm not really even going to worry about it because it doesn't really matter to understanding what RMS is. So root, square root, mean, average, averages, means, and squares to the power of 2. Don't worry about the mathematics of this. We're not going to talk about it anymore. Instead, we're going to kind of go to the fundamental definition of what the math actually produces in terms of physics. So, what kind of brought this up? Well, I opened up my cabinet over here and I saw that I had this unit right here in the cabinet. What's this? So this is looks like a little heating device, right? This is a heating plate, a hot plate, a burner, a little portable burner unit. This was actually my grandmother's, and she used it for cooking outside sometimes, outdoor type environments. And I don't know where she obtained it or where it came from originally, but this was probably made in the 1940s or 50s. I'm just going to say that based upon the fact that it's got a nice nameplate on the side here, and it's got a nice asbestos insulated cord with a cotton covering on it, so you don't see that anymore. And the nameplate states that this device is a Model 10 A&H Electrical Products from Brooklyn, New York, that can produce 1200 watts with 115 volts AC or DC. Doesn't matter whether it's AC or DC. As long as it's 115 volts, you'll get 1200 watts out of it. Interesting, right? That's very interesting because we know that AC and DC are very different from each other. So with AC power, like if I was to stick my oscilloscope in the wall socket over here, I would see a waveform that looks kind of like this, you know, up and down, up and down, up and down, just like this board. And the voltage that I'm measuring obviously oscillates between here and here, positive to negative, and everything in between, right? It's like a circle going around, the sine function, you know, going all the way up, down, 60 times per second, 60 hertz. Here in the United States, other countries might be doing 50 hertz, but in reality, the result is the same. It works the same way. But direct current, if I was to stick my oscilloscope in a DC wall socket, if there was such a thing, back in the days of Thomas Edison, I would see a voltage that looks like this. It's just going to show me a straight line on the oscilloscope. A line. And the difference between this and this is the voltage. Let's say it's 115. All right, 115 volts. Just like the hot plate says it takes on its nameplate. But if we look at the AC, the difference between 0, this is 0 and 0, and we'll dash the line, is not 115. It's more like 100 and, I don't know, 62 or something like that. But how in the world is that possible that if I plug that hot plate into AC or into DC, it gives me the same power output? Well, that's the RMS. So this is constantly oscillating between positive 162 volts and to negative 162 volts. And in between, you have everything from 162 to 0 to a negative 162. And averaged over time into a resistor, this comes out to the equivalent of 115 DC. So we got 115 DC. So the definition of an RMS, voltage or current or power in electricity, is the AC that gives me the same exact power dissipation in a resistor, like a stove or a heater, as the equivalent voltage in DC. So 162 volts peak, from 0 to peak in AC, is equivalent to 115 volts from 0 to voltage in DC. And therefore, when we tell you that your wall socket has 120 volts or 115 volts, it actually has 160 volts or 170 volts peak, but the average voltage in terms of resistors, resistive load, is 115 or 120. So that's what RMS actually is. It's the DC equivalent of the AC. And when you have an audio amplifier that says it can put out 500 watts RMS, what that actually means is that it can put out the equivalent of a continuous DC power output of 500 watts. So if the audio signal were to be set such that you would be giving it 500 watts of straight 100% continuous DC equivalent power output, 500 watts, that's how much that amplifier can generate. You can see the RMS rating of an amplifier or a speaker is an extremely conservative value. Okay, it's because music is alternating current. It's extremely variable, and there's loud parts, there's low parts, there's all this different variation in music. And music actually has a relatively, generally a low average power to peak power ratio. So you got like the real crazy drum sessions in music, or the guitar riff, or the really active parts of the music. But then you've got all the other parts where it's just like lyrics and a little bit of instrumentation and all that. The average power is far, far below the peak power in music. And that's why an amplifier that's rated in RMS can actually generate a lot more power, assuming it has enough power supply to do so, to make music very loud, because music has a very high peak to average ratio, or a very low average to peak ratio, as confusing as that might be. So basically, RMS is the DC equivalent. It's the amount of power or voltage that you would get from a resistive load fed from the DC voltage of the same value. So this gets complicated with certain kinds of electricity. So a sine wave, which is what we get from the electrical utility, we get from the wall socket A sine wave, mathematically, it comes out to the RMS ratio is a square root of 2. Easy, right? 1.414 is a square root of 2. So if I'm getting 120 volts out of the wall socket, RMS, that means that the relationship to the peak voltage is basically the peak voltage divided by the square root of 2. 100 is about 170 volts peak voltage divided by a square root of 2 divided by 1.414 gives me 120. So in a lot of these multimeters, you buy a multimeter like this. This is a $5 multimeter, and you set it to the AC voltage section of the scale. You stick it in a wall socket. What this is actually measuring is peak voltage. So it's actually measuring the sine wave voltage from 0 to 170. Okay, that's what it's actually measuring. And then it basically does the math and divides that by 1.414 or multiplies it by 0.707. I don't know how they did it in here. And it says, oh, you got 120 volts at the terminals, at the test leads, right? Okay, that's the $5 version. But then we've got the true RMS multimeter. So this is a Fluke 175 true RMS multimeter. And it is designed to actually account for different kinds of waveforms. So if I was to stick this in the wall socket, it would say, oh, this is a sine wave, you know, and it would calculate the average, the RMS voltage from a sine wave. But if I was to go out and stick it into the outlet in a cheap Walmart $20 special power inverter that creates a semi-square wave that looks like this, all right, it's going to be a different ratio between the peak voltage up here at 0 and the RMS, or what you would get if you plugged a heating element into the inverter. So those inverters are actually designed where the RMS voltage is 120 volts. So you plug a heating element into it, or an incandescent light bulb, or something simple like that, it's going to give you the equivalent amount of power as if that was DC 120 volts. Or if you plugged it into the wall socket with a sine wave, it was AC 120 volts. But if I measure the peak to 0, it's going to be something weird. It might be like 150 or 140 or 100 and maybe even 190 or something crazy like that. And this meter will mathematically figure out what that value should be based upon the type of waveform that's being fed into it. This is a, you know, hundreds of dollar multimeter. This is a $5 to $10 multimeter, right? So that's the difference. The computational capacity of this one is much higher than this one. But in reality, only somebody who's really measuring this kind of weird waveform needs something like this. But your average homeowner can get by perfectly fine with something like this, the cheap one, right? So I would expect, I mean, they have come down in price. This, I'm just guessing on the prices, but something like this years ago was almost like unobtainium. Like you couldn't even get things like this. Now these are pretty widely available for pretty reasonable price. Now Fluke is, you're paying for the brand name. It's kind of like buying a Gucci handbag. You're paying for the brand name and the quality, but you can buy a true RMS multimeter that is cheaper than these, but it does a lot more computation versus just applying a static factor to the measurement. So that's basically it. Understanding RMS. RMS is nothing more than direct current equivalent heating power. So if you're heating up a tub of water, a pot of water on a stove, let's say it takes 5 minutes to get that water from 70 degrees Fahrenheit to 212 degrees Fahrenheit before you start boiling the water. On a RMS voltage, you want to have, okay, if it takes 100 volts DC to boil the water in 10 minutes, then what is the voltage of AC that takes 10 minutes to start boiling the water? That's the RMS value of that AC peak voltage. So if it's 170 volts, the RMS comes out to be about 120, 115, 120 range. So that's really all it is. It's a fancy average. Is all that RMS is, and it was developed as a way to ensure that we can compare DC to AC and average powers out when you've got a time varying waveform. Power delivery into a resistive load in relation to a constant DC voltage applied to the same resistive load. Hopefully that's clear as dirt and hopefully helps somebody. RMS, root mean square. That's it.